Section 10.4 is covering the probability of disjoint and overlapping events. So the first thing we need to do is define disjoint and overlapping events. And the best way to do that is to use Venn diagrams. If you'll remember, Venn diagrams are these diagrams with ovals that represent sets. And those sets, sometimes they overlap and sometimes they don't. So things like set A could be children with cats, and set B could be children with dogs. And so some of those kids that have dogs could also have cats, so they would be in the middle. Whereas a disjoint set might be children with pets and children without pets. And so there's no way that those could overlap. If you do, then you don't. Okay? So this is how overlapping events, you might be involved in both sets, or you could just have cats or just dogs, okay, but you could have both. Whereas if you either do or don't have pets, that's going to put you in two completely different circles on this set. Okay, let's see how that affects our probability. If we have compound events is what we're dealing with here, and that's compound events deal with more than one set, and that's why we need to recognize the different sets in the Venn diagrams. So a union, if we're talking about a union, that's using the word or. And that means I want anything that's in A or B. It doesn't matter. It could be in both, but if it's in A or if it's in B, that's what I care about. If I want the intersection, I'll say I want the probability of something that's in A and B. That's trickier. That's exactly this. It has to be both A and B. It has to be this intersecting part. All right? So first what we'll do is we'll talk about disjoint sets. So this would be where they don't overlap. So we don't have a problem here. So if the two sets of whatever it is that you're finding the probability of, if the two sets are disjoint, means there's no overlap at all, then we simply find each probability separately and add the two probabilities together. Such as, if I have a set of cards and I want to know what is the probability of drawing a 10 or a face card. Well, in this case, the 10s are in this set and the face cards are in here. There's no way for a card to be both a 10 and a face card. So what we do is we decide, okay, well, the probability of a 10 or a face card would be the probability of the 10 plus the probability of the face card, right? So the probability that it's a 10, there are 4 10s in a deck of cards, right? So the probability that you get a 10 would be 4 out of 52. And the probability that you get a face card, well, there are 4 queens, 4 kings, and 4 jacks. So 3 times 4 is 12. So there's 12 face cards in a deck of 52. So you add those together and you get 16 out of 52 is your probability that you will draw either a 10 or a face card. And then you would reduce that down, and you can even divide it. And so 0.308, I believe, is when you divide that, what you get. So take 4 divided by 13, that's what you get for your probability. So the probability of drawing either a 10 or a face card is 0.308. What happens if there is overlap? If there is overlap, what you're going to do is first do just what you did. You're going to add each individual probability, but then you're going to subtract out whatever is overlapped, okay? So if you have let's just look at one. So if you have if you want to know the probability of drawing a face card or a spade, well, you've got face cards. You've got face cards that are the jack, the queen, and the king, right? So you've got, but then if you've got spades, you could have a jack that's a spade. So that would be in this middle part here. It's both. It's both face card and it's a spade. So here's what we're going to do. If we take the probability of drawing a face card or a spade, what we're going to do is we're going to take the probability of drawing a face card and we're going to add the probability of drawing a spade. And then we're going to subtract the probability of a face card that is a spade. So a face a face spade. Okay, face and spade, so both of those together. So what we've got, the probability of drawing a face card, we said the probability of a face card is 12 out of 52. And the probability that you'll draw a spade is, aren't there 13? Yeah, there's 13 of each suit. So 13 out of 52. And now what happens is some of those are overlapped. You've got 12 face cards, you've got 13 spades, but there are 3 face cards that are also spades in this middle part. So you're going to subtract 3 out of 52 because we added those in twice, because we added those here and here. So when we take 12 plus 13 minus 3, we end up with 22 out of 52. And then you can reduce that and divide, and you should get, that's roughly equal to 0.432. So if you've got an overlap, you're going to add together what you've got, the 2 different probabilities, and then subtract out the overlapping part. All right, so now what happens if you've got an intersection? So here we're dealing with an intersection here. Sorry. The intersection is A and B. So if I want both, and, then that includes what's in the middle here. Let's look at a problem with that. So if I have 100 students, 92 own either a car or a computer. 65 of that 100 own cars, and 82 of that own computers. So what we're going to do in this case is, what I want the probability that they own a car. So what happens is they have to own both a car and a computer. So the ones that own cars are 65 and the ones that own computers are 82, but some of them might own both a car and a computer. That's the part I want to know. Where is the overlap? Where's the overlap here? So what's going to happen is this. We're going to take this equation, and we're going to put in the parts that we know so that we can find what we don't know. So we know the car, so we're going to take the probability of the car plus the probability of if they own a computer. Then if we subtract out that intersection, right? So the probability that they own the car is this part. If they own a computer, it's that part. The in-between area is owning both. So we're going to take out the probability of both, and that's going to equal the probability that they own a car or a computer. Okay, does that make sense? So if we took out the ones that have both, then we end up with the ones that have either or. Okay, so now we have our equation, and we can figure out the parts that we know. The probability that they own a car is going to be 65 out of the 100 students. The probability that somebody owns a computer, well, that's easy. That's 82 out of 100 students. We're going to subtract out the ones who have both, but we don't know that. We don't know how many of them own both. So that's going to be our X, and that's going to equal how many own a car or a computer. And that's what we have here, 92 out of 100. So now it's a simple equation. So the 65 and 82, 8, 9, 11, 8, 9, 10, 11, 12, 13, 14, 1, 47 over 100. Subtract that. Actually, you know what I'm going to do? I'm going to add the X to both sides and subtract the 92. And if I subtract that 92, what does that get me? 55, 9, 10, 11, so 55 out of 100. So my probability is 0.55. So the probability that someone will own both a car and a computer in this group of students is 0.55. Did I go down? Oh, good. Woohoo, looky there. All right. So far, so good. The trick is that you've got to think through, okay, is this both? Is this and? Is this neither? Is this or? Because now what we're going to do is we're going to, okay, sometimes it's easier Sometimes it's easier to go backwards. So, oh man, I messed up my writing here. That's okay, you can still read it. The complement of a probability, it went away, I messed with it. The complement of a probability is A, you read this A bar, it's just A with a bar over it. So what this means is the probability of A bar equals 1 minus the probability of A. So what we're saying is this, the complement of the probability of something happening means I want to know when does this not happen, okay? So what we're going to do is we'll take, well, if, remember 1 is you get a probability of 1 if something is certain to happen. So if you take the 1, if it's certain to happen, if you take the 1 and subtract off anything that is probable, then what's left is what is not probable. Does that make sense? So if I want in a deck of cards, once again we're dealing with just a deck of cards, if I want to know what is the probability that we will not draw 7, if you've got the deck of cards laid out there and you just draw a card, what is the probability that you will not draw 7? So in this case, this is the probability of bar 7, okay, the complement of 7. So what happens is I want to know, I want to take 1 minus the probability that you draw 7, okay? So if you, because that's easier, it's easier to figure out, well, what's the probability of drawing that one card than having to figure out what's the probability of drawing all of the other cards. It's just quicker and easier this way. So 1 minus the probability that you will draw a 7 is there's 4 7s in a deck, so it'd be 4 over 52. So 1 is 52 over 52, so you got 48 over 52. Oops, 252. And if you divide that out, it should be 0.923. So you have a 923, or I guess a 92% probability that you will not draw a 7. Okay? So now if you want the probability of not a red face card, that would be the same as probability of red face bar. That's not a number, so I'll do it that way. Okay, so what you'll do in this case is the same thing. So you're going to take 1 minus the probability that you get a red face card. So a red face card, there's going to be red face. So there's the face cards, you know, there's three face cards, a jack, a queen, and a king. And there are 2 suits that are red, diamonds and hearts. So you have 6 cards that would be red and a face card. So you've got 6 out of 52 that you will get a red face card. So the probability that you will not get a red face card is just 1 minus the probability that you will get a face card. Okay, so 1 minus 6 over 52 leaves you with 46 over 52, and if you divide that out, you get what do you get? 0.885. All right. Okay, so now one more. Let's put this into a word problem, and this is where you definitely want to get out your calculator. You're not going to want to do these by hand. Here we go. So if you've got 10 people at a party, what's the probability that at least 2 people will have the same birthday? So what I want you to do is, this is one of those cases where it's going to be easiest to use the complement instead of figuring out, okay, at least 2 people have the same birthday. That's 2 people have the same birthday, 3 people have it, 4 people, that's a lot of numbers. So instead of going forwards, let's go backwards, and let's say, what is the probability that nobody will have the same birthday, right? That would be easier. So we're going to take 1 minus the probability that that 2 people have the same, or that at least 2 people have the same birthday. Okay, so we're going to take 1 minus 1 minus the probability that none have the same, and that will give us They all have this, or at least two or more have the same. So here's what happens with this. Okay, check this out. This is crazy. It made my brain go wild. The probability that nobody has the same birthday is going to be, so we're going to put our 1 minus over here. And this is going to make your calculator even go crazy. So you've got 10 people. So you've got to count for all 10 people. So what happens is, remember, it's the probability is the top gives the favorable outcomes and the bottom is all of the outcomes. So the bottom number is going to be, there's 365 days to the 10th power. That's how many possibilities there are. Okay, so the top number is going to be favorable outcomes. So what you've got to do is you've got the first person has 365 days that he can have a birthday on, right? And then the next person can't have all 365. They've got to have 364. And let's ignore the fourth. Okay, I know somebody's saying, but there's a fourth. Let's ignore that one. That'll drive us crazy, even crazier than this. So what happens is this. You've got to go down 10 times. 363, 362, whoops, 361, 1, 2, 3, 4, 5, 360, 359, 358, 357, 356, and I think that should be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. So what you're going to do is you're going to put these into your calculator and it's going to give you some gosh awful craziness. But when you divide it then by 365 to the 10th, then you're going, and what you can do is even you can reduce it by 365 and make this 365 to the 9th. And I think I had to do that because 365 to the 10th wouldn't fit in my calculator. It gave me an error. So if you take it to the 9th, and maybe it wasn't that, maybe it was the factorial. One of them was just too big. It wouldn't even take it on my little calculator. So punch all of these in, divide by 365 to the 9th power, and then you get 1 minus point, I think it was 883. Yes, 0.883, or roughly that. So the probability that in a party of 10 people, and that's not even a very big group of people, the probability that you're going to have the same, that at least 2 people are going to have the same birthday is 0.117. All right? Whew. Here we go. I think there's only like 1 like that craziness. I won't make your life too miserable. All right, probability, here we go. See you later.